using the rule of differentiation, we find that this equals, when differentiating, so d dt.
Yep.
What?
I mean, yeah, not there, but
Oh, you're
I
right.
would.
You're right. Let me. I'll
Here, you put the D.
Nice handwriting, though.
Yeah, it's a good brackets too.
Okay. So A would equal d dt of all of this. Right?
Okay.
So A would equal
I think it'll make your life easy to distribute that mg over b first, and then.
skip steps.
Yeah. Okay.
Wait, why would you distribute? It's a constant. You can just pull it out. I think.
Yeah.
I don't know what happened.
Yeah.
That's just.
You have to.
So I,
It'll be the same.
Okay, I see where you're going.
Oh yeah, you time e to the e to the negative e over.
Don't forget there was a negative originally in front of that e.
Right,
Oh,
so it's
you're right.
positive.
E and M cancel out. A with G e is a negative e over M.
So, couple things. What happens when t is very, very small? Let's say t is really close to 0.
Oh, as it approaches 0, it goes
One.
the whole
So my acceleration is
0.
g. And that makes sense because physically,
But it's multiplication, not addition.
Wow.
So shouldn't the dt is g as well?
no, because there's no g, there's no t multiplying g. The t is in the exponent of e.
Oh.
So,
no, you're asking when
if
t
I,
approaches 0.
yeah,
The whole
as
step.
t approaches 0, which means, physically, what does that mean? What would that look like? My t's being very small.
It's the beginning.
The beginning, near the beginning of this whole falling thing, I'm falling pretty close to free. You can sit down if you want. You're cool. I'm falling pretty close to free fall, right? What happens to my acceleration as t starts to get really big? As t approaches infinity. I don't need it to get to infinity, but as it gets really, really big, what happens to that function?
Exponential increase.
It's gonna be really, really big.
Is it?
E to the infinity.
Well, I said as
Negative.
t goes to infinity, as t gets bigger, but that's not just e to the t. That's e to the negative some stuff t.
Right.
It's going to approach 0,
E is like that here.
which means as time goes on, my acceleration function goes to. What does my acceleration function go to as time goes on? No. 0.
That's where
It goes to 0. Yeah. And that makes sense, right? Isn't that what we said a little while ago? Right? So our math at least is very consistent, and it totally should be, otherwise it wouldn't be physics, but it's very consistent with what we intuitively know terminal velocity should do, right? That's a great way of double checking. Look at your equations and see, does this physically do the thing that I need it to do? All of our mathematical equations need to be physical. They have to be. Like, math doesn't have to represent something physically. It doesn't have to. Physics has to have physically representative math. It has to, period. There's no room in physics for not physical math, except like Dirac delta functions. I don't know why, but that's a thing. I don't know. These weird delta functions that are 0 everywhere and infinite at one very specific point. Like, it's weird. I don't know. We use them in quantum. Who wants to draw this graph? Can anybody tell me what this graph looks like?
Johnny,
Kind of, yeah.
Yeah.
It's gonna be E.
No, not in the air. Draw it over there.
No, that's not gonna be good. See you.
Oh my God.
I'll do it, but.
Yes? Thank you.
I knew it.
Wait,
Can you do it right on the side in that empty spot? Yeah. It's not bad. It's not that bad.
No. General ideas.
What color?
You could do blue or red. Green is hard to see, but blue or red is good.
I mean, we don't know the constant, so wouldn't you just
We don't, but we know for sure that what's on my x-axis?
did math into it?
No, but what measurement is on my x-axis? If I'm trying to graph acceleration, yeah, time. So that probably tells me I'm not doing anything in the second or third quadrant.
Right. Yeah.
That's okay. You can keep them there.
Okay.
It's not really it doesn't hurt us.
Because it would be like this.
Uh-huh.
What do you end up with like whatever it's approaching.
Yeah, okay. That's reasonable.
You need to put like G.
Do I have to put an asymptote? Because that's
Well,
what
where
I
is the
have
asymptote?
On that.
Yeah, the asymptote. So you're really approaching 0. You're not getting to 0.
It has to be 0.
Yeah.
With
Yes.
okay. I want to cross the steps.
What is the y-intercept?
G.
Simi, you sound so. Are you sick, Simi? Like, are you okay? You sound very raspy and. You want tea? Like I can.
Really?
I have tea if you want. If you want tea, but I can make you some at lunch if you want.
Wait.
Y is the intercept G. Who can tell me what happens to that function when t is 0?
Never mind. I got it.
So this is a really important type of problem. What do we kind of get from this problem? Got an ugly integral. It actually isn't that ugly, but we got an ugly integral. Hold on. Where'd you go? There you are. We got an ugly integral. That really only looks ugly, but it's like a very easy u sub. That's not a big deal. But more than that, the bigger part here, we dealt with this ln stuff. Don't forget your properties of logs. And we transformed this into something that's a little bit easier to read and something that's a little bit more intuitive. This exponent, where did I put it? Right here. This exponential thing here that gave us a function of v. The problem before was that this was a function of t. That's not good. I didn't want t equals. I wanted v equals. What's up?
Isn't it negative g times
Well, two things. Number one, originally I defined down to be positive.
No,
So-
but there's go to the last slide.
So that's the first thing. So I expect the acceleration here net is downwards. I'm expecting, without doing any math, I had set up everything to give me down to be positive. So I'm expecting a positive answer. Now when he did his math, he skipped in here there's a little step, a couple steps that he skipped. Distributing this constant into the 1 and then taking the derivative, that dies, right? That goes away. Not a big deal. No, you don't want to. I'm just saying it's gone. I'm not saying you have to. I'm just justifying why it's gone. It's gone as the constant, and that 1 doesn't do anything. But then here I had a negative. When he took the derivative of this negative b over m came down, and the negative canceled out to make it positive. So I'm getting mathematical proof that the answer is also going to be positive. This is good. I expected it to be positive because I'm expecting it to start at g. That's kind of my gut reaction. I wanted it to start at g. If this would have given me something that did not start at g, I'd be panicking. I really would be. Because I feel like, it starts at free fall for at least a very small amount of time. I need it for at least small t's to be pretty close to g. Pretty close. What's up?
So are you saying that it never reaches terminal velocities when we approach?
No,
'Cause
it's not. It's a horizontal asymptote,
Yeah.
right? It can cross it. It doesn't cross it. It gets to it. It reaches that number, stays at that number.
I thought you can't cross it.
You can cross horizontal, not vertical.
You can cross horizontals. You can't cross. You can't touch. You can't get on vertical. And what's the rule with skew or slant? I don't remember what they call them anymore.
Horizontal axis can
Yeah,
cross
you can cross
the
it.
number that it wants to be near the end.
Yeah.
That you can, if you look at the graph of sine of x over x, it goes over and under and over and under, and it's like a water ripple, and it starts up high and it kind of settles down. The more to the right you go, the limit is 0. So that is considered the horizontal asymptote. You cross an infinite number of times.
Yeah. So, questions. This is a big problem. We spent a lot of time on it, but it's a good problem. The graphs are also really important. The velocity graph, number one, big thing, because I've seen some sample problems with this, and they'll give you, especially in the multiple choice. Oh, here are some sample graphs for an object in terminal velocity. What would the velocity graph look like? Notice that this guy here is not linear. It's not. if it was linear, what am I implying about the acceleration?
Never is linear.
No.
It's always. Wait,
No.
What are you implying
Oh,
about
no,
the-
that it's
that it's constant.
That it's constant. If I at any point have a velocity graph that has a region that's linear, I don't mean constant. I don't mean horizontal. I mean linear. That means that at that region the velocity is constant. It stays that number. But we know that the velocity, number one, changes, but the acceleration changes. We know it changes for sure. So it cannot be linear. Now, are they going to give you something that's quadratic and then exponential? Like, it's really hard to tell, right? It really is. So you're looking for something that is curvy, right? But approaches this VT value. And this is another one where it will reach this value and stay that value.
What was your terminal velocity? I think it's
Our number was not a number because we did everything here symbolically.
oh yeah.
Mg over b. Mg over b.
If you do the limit for the velocity.
Yeah, and we did that very not mathematically, where we said as t gets really big, right, as t starts to blow up, this thing reduces, and this part of the function goes away. All that's left is mg over b, which was our terminal velocity expression from our forces and analysis before.
Can you go to
The A one?
A versus T graph?
There we go. Now this one, you'll probably see it a little bit more dramatic, where it'll like curve down, it'll start up real high. It doesn't matter. The point is that it is curvy, right? It looks like an exponential graph, and it approaches 0. It's not a linear graph that goes straight down and then goes to 0, because if it was linear, things would be really weird, actually. If it was linear, that means that the jerk is constant, and the jerk can't be constant, but whatever. All right. Questiones. That's an Italian dessert, if anybody's wondering. No, I'm kidding. It's totally not. It's Mexican. No, I'm kidding there too. 60% of the time, 80% of the things I say are 100% false. So
60% of the time.
every time I say that, somebody has to repeat. All right, let's keep going. So let's look at the elevator problem. This is the second of the 3 special cases we have left in your homework set. This is problems 37, 39, and 40. The book doesn't have a ton of them. I'm trying to find more problems for you to do. But I'm broke right now, so I can't buy more stuff for you. I'm trying though. But I have some ideas. Now you see me. Now I'm in jail.
Great movie.
I want to see the second one. The first one was really good. Yeah. Okay. I want to see it.
Yeah, it's great.
So, for a second, as you're writing this, I want you to just kind of think about your experiences in an elevator, because I'm sure everybody here has been on an elevator at least once in their life. And when you get on the elevator and you press a button, the top floors, and the elevator starts to go up, what do you feel? You feel heavier, right? You feel your knees kind of buckle down a little bit, just a little tiny bit, and it kind of feels like something's pushing you down. So you feel just a little bit heavier. And if you were on the top floor, making your way downtown, walking fast, strangers past and you're homebound, what do you feel on the elevator downwards? You feel lighter. You kind of feel like you kind of come off your feet just a little tiny bit. I don't know about you guys, but when I was younger, I had this huge fear, and by younger I mean still now, getting off the elevator like it falls as I'm halfway out. Like that's a huge fear of mine. And the other one is when it starts to go down. I watched I don't remember what movie it was, but it scared the bejesus out of me. Like I was like, oh my god! I took stairs for a long time. And I had friends that lived like on the 15th floor, and I was like, I'm not seeing you. Like bye. All right. So as you go down, you feel lighter. Okay. What happens when the elevator, like if you got a really long elevator? So yesterday I tutored this kid who lived like on the 40th floor of some building. And after a while, like the first couple floors, you're like, yeah, I feel a little heavier. But that kind of levels out, right? And it's moving at a constant speed. What do you feel? You kind of feel normal. You feel nothing. So you feel normal. Not the force, you do feel the normal force, but you feel regular. You feel like you normally feel on your everyday life. And the question is, why does this happen? Why do elevators make me fat? Why can't I live my life always going down? Joke's on you, my life is always going down. Sorry. Let's break this up and look at it in pieces. We'll look at the going up part, we'll look at the going down part, we'll look at the constant part. So imagine you're on an elevator and you're standing on a scale. Because if you're feeling heavier, right, I'm expecting that my scale will get different. That's kind of if that's what I'm feeling, that's kind of what I'm expecting to see. So if I'm moving up, let's think about the forces that are happening on my body. Because feeling heavier means what thing is changing? That's the big picture. But what thing? If I feel my weight, I feel like my weight would change. Except my weight, as we saw, is dependent on what two major factors? Mass and gravity. And yeah, being on this elevator does not change my mass and does not change the acceleration of gravity. So how is my weight changing? Well, let's draw the forces acting on this kid. Guy, person. I don't know, man. It's a comic.
The first one is
This guy's at rest, yeah, and then he starts to move up. Granted, I could not find consistent pictures, and I am not an artist, so I found the best that I could. All right, so here is my blue da-ba-dee-da-ba-die guy. What forces are on him? Her, it. Normal. Now which way does normal go? Number one. Up. The normal goes up. But let's be kind of picky. And I'm going to do this in green. Where exactly does this normal force come from? From the scale. The scale is what's providing this normal force. And that's important. That's an important distinction to make. Well, he's standing on the scale, right? So the scale is the surface that's providing that normal force. You'll see in 1 second. It would be the floor. But the thing would still be true. But we're going to build to something. What other force is on him right now? Gravity. Pulling him down. And I'm just going to call that this person's weight. And is there anything else touching this person? No, not really. Now, as this person accelerates upwards, does anything new touch them? No. So nothing new touches them, but their net force changes. They have an acceleration now. Not only does the elevator go up, everything touching the elevator goes up. Everything in the elevator goes up. So here, in this particular case, if I write my sum of forces, what would I get? Equals 0. Okay, that's boring. And that just tells me that what I weigh is my normal force, and when I'm at rest in an elevator and the elevator's not moving, we just said we don't feel anything. That's not a big deal. On the person? Yes, but I care about the person. That free body diagram represents the person. So now let's look at this case and see how that differs. There's my person dot. What forces in this situation, as they accelerate up, does this person feel? Still the normal. Right? And that normal force is still coming from the scale. Okay? And what other force? Weight. Going down. There's actually no reason why these arrows are different. Not really. I'm just drawing them different. Weight. But if I draw a sum of forces, a sum of forces here, what I would get is the normal plus the weight equals, it no longer equals 0. It now equals ma. Now this is why it's important to know where that normal force comes from. Because if I take a look at the scale, and I draw a free body diagram for the scale, the scale feels how many forces?
No, 3.
3, it'll feel a normal force from the floor, pushing it up, right? So it'll feel a force normal. This is coming from the floor of the elevator. I'll call it that. That's fine. I'm okay with that. And the weight of the scale. Well, it turns out with scales, it measures, that number that the scale gives you measures your interaction with the scale. Does that make sense? You step on it, it measures how much you are stepping on it. What force here represents how much you are stepping on it for the scale? Yeah, this force represents your interaction with the scale. And it happens to be a third law pair force with that force. Your normal force up. So the amount that you interact with the scale is the number that the scale tells you, right? And it's that normal force that's on both of you guys. This is good. Because if I feel heavier, the scale should tell me that my numbers got bigger. That's what it should tell me. I feel heavier. It should tell me bigger. And that thing that it's measuring is that normal force right there. And with this equation, I could set up an expression for that normal force. I could say all I did was move over weight to the other side. And what I get, if I simplify this a little bit, notice that if I take A and I add it on to G, what happens to that term? It gets bigger. So that normal force is a number that will be bigger than my weight. And that normal force represents how much I am interacting with my surface. And that represents the number that the scale is going to give me. This is the reading This would be the reading on the scale. It would give me the proof that I am actually getting heavier. Right? Does that make some sense? What's up?
Can't you reason about this a lot more simply by not looking at the forces, but looking at the acceleration, and you just add A and G, which is your total, you get your net acceleration of that.
But what allows you to do that? What allows you to do that?
Well, behind the scenes, that's what it is.
Yes, that's true.
But you could have just wrote sum of forces equals M times A plus G, which is what you did after.
No, because sum of forces does not equal that automatically. That's not a thing I can say.
Your net acceleration. It's mass times your net acceleration. And you know your net acceleration because you know each of them.
What happens if I have more forces here?
Well, all of them experience net acceleration.
That's true, but what happens if I had a tension here? The person's holding a rope up. Then things start to change. Oh yeah. The more terms I start to add on to this, the more my net starts to change. So you can't just skip those steps. You got to prove those steps.
So the AP requires.
Yeah, you need to justify where, because what happens if you're wrong? Now they can't give you that point anyways, right? If you make a mistake in your thought process, then you lost all possibility of getting any points, right? And that's not even just for AP, like in life. Like don't take 3 steps forward if you can't justify those first 2 steps. You know what I mean? Because then you never know, you might fall into a hole. So what we could say, is that whenever the elevator moves upward, we feel heavier. What that means is that we have an apparent weight. And that's the key here. Apparent. It's not actually our weight that's changing. Our weight stays the same, because as we said, M and G are constants for us. But there's this new type of weight, this new quantity that kind of, it's like a pseudo weight, not sumo, but pseudo weight that we call apparent weight. And we say that weight gets bigger. And the reason why it gets bigger is because we get this relationship. That's how much bigger it gets. Versus when it's just mg. Just like if you were in a rocket ship and your rocket ship started to accelerate up, you would feel something very similar. You would feel yourself get really heavy. And this is why. You'd feel yourself get really heavy because what you're feeling is that interaction, right, with the surface, that normal. I feel like we're all really clever, so we kind of know what's going to happen when we go down. If I go down, now in this case, what's going to end up happening, I kind of already have a free body diagram. Normal plus this negative mg is going to end up equaling negative ma. And if I solve for that force normal, again, that interaction normal is with, it's normally with a surface, and it could be just the regular floor. Notice that you still feel heavy, even if there's no scale on the floor. There doesn't have to be a scale. But it's really just there to verify that this is what's happening. And in the physics problems, it'll always say, oh, a student is on an elevator standing on a scale. Because in order to get a physics PhD, you have to carry a scale with you every time that you get in an elevator. It's a law.
Why are you telling me looking negative?
Because this object is accelerating downwards, so it should be negative for down. And if I do this, oh, well, yeah, sorry, wrong. Yeah, I got it. And that number is going to end up being smaller than my weight. I'm going to feel, I might as well just press next. I'm going to feel an apparent weight that is less than my normal weight if I'm accelerating downwards. The MA, this MA, comes from the fact that I am accelerating down. You can think of it as, this is the net force, but it's really the elevator accelerating downwards. That's what it is.
Why can we write it for the other PT?
We did, well, I did not draw it, but we did write it. Equals MA.
Oh.
This thing, you on free body diagrams, you don't actually include net forces. You don't include components either. So this picture isn't actually a free body diagram, but I'm going to take it as if it's mostly a free body diagram, and I'm going to kind of ignore this arrow and just take it as a suggestion of you're moving in that direction. That's really what I'm doing. I'm going to recopy this on the next slide. So then I'll get okay, that's going to be if I'm accelerating downwards. Note that in all of this, I said that we are accelerating in these directions. Does that mean that I have to be moving in those directions? No, just keep that in mind. Just keep that in mind for a second. Can I go to the next one?
For consistency, would it make sense for the other one to say G plus A instead of plus G? So that you're like
Okay.
subtracting degrees of gravity.
Wait, can you go back?
Oh, too much.
What other situations other than elevators would this apply?
Any non-inertial reference frame. Any reference frame that is accelerated. Because that's really the difference. The elevator is a coordinate system itself, right? And that accelerates up or accelerates down. So if I was like in a rocket and the rocket accelerated up, I could use this same thing. Or if I was in a race car and the race car was vertical or like on a ramp, you know.
Like if you're going up in a plane, and you're going.
Yeah, okay. As long as I have some type of, I need heavier
You would
happens
have to
up down.
put in the components
Yeah.
To account for the.
Yeah. I would need some type of up down. The race car doesn't necessarily make you feel heavier. right? It pushes you back. So you feel a force that pushes you this way, which is doing the same type of thing here. It really is big picture. It's an inertial frame or a non-inertial frame that's pushing you in a way. But this is specifically giving you an apparent weight because it's happening in the vertical where our weight is happening.
An airplane is a good example. Like, it's a really interesting problem because you're also slanted, so you have like the ramp.
Yeah, so that's what she was saying. You would have to find the component stuff. And
Yeah.
it's an interesting one. What if I was moving at a constant velocity? And in this case, not super fun. I've got kind of a free body diagram a little bit better here and a good one here. What does this sum to? 0. And in this case, oh, whoops. I got if I'm moving at a constant velocity, and again, does it matter if I'm going up or down? No. As long as I'm going constantly, I'm going to feel normal. I'm going to feel my normal, everyday, regular weight. I wish my life was always a downward elevator. Making me feel better. Can I go next one? So, if the elevator moves at a constant velocity, we feel no difference in our weight, and we can say that our apparent weight is exactly the same as our real weight. I guess I'll write it again here. That's kind of the situation we live in all the time. All the time.
And again, for consistency, it's the m times g plus 0.
Yeah.
I'm just showing this the formula is the same. Just replacing that a with
Different values.
value and a value or 0.
There's a special value. Ho ho.
Your net acceleration.
Ho ho ho. Can I go next? So just summing it all up, I found a really cool graphic that I liked. And remember that I did say accelerating up and accelerating down. And we agreed that does not mean that I have to be moving up or down. So I could be moving up and accelerating up. And if I do that, here I'm going to get heavier. I'm going to get heavier in that case. But if I'm moving up at a constant velocity, I feel nothing. I feel the same. If I'm moving up and I'm slowing down, my acceleration is negative, here I'm going to feel lighter. And then I can do the same thing here. If I'm going down and I'm accelerating down, I'll feel lighter. If I'm going down and I'm moving at a constant velocity, I'll feel the same.
You said for the third one that you're slowing down. But
Yes.
Not necessarily. Right?
Well, number one, they use the word decelerate, which I don't like. It should be accelerate with an arrow pointing downwards. That's what it should be. But they wrote negative a, so that's cool.
Could be, speeding up.
The only way to speed up is if your velocity and your acceleration vector do what?
The same.
They not the same. They point the same way, right? So if the acceleration vector here points downwards, but I'm still moving up, I am slowing down.
Oh, you're moving up.
Yeah, so all of these are for moving up, and all of these are for moving down. And if I'm moving down, but I am decelerating the way I'm moving down, which means I'm accelerating up, that means I'll feel heavier. So avoid these two for Thanksgiving. Or my everyday life. Calculus?
My
BC people?
what does this remind you of from last year?
About the velocity and acceleration of the particles.
What is it? I don't know. What about? Oh God.
Where they're moving, they're it.
Remember those buttons speeding up, slowing
Yeah,
down?
that's what oh, that was the thing of minimums and that.
No, it's not the signs.
What? Yeah, I know what we're talking about. Just if they're opposite, they're slowing down. I'll pass me.
I don't know wasting time, but they're actually connected to that. Yeah. If the acceleration and the velocity are pushing in the same direction, then
Work it out. Just prove it. It is, but still. Give it a second. But now keep it to yourself now. I hope nobody else heard you. And if you have an answer, keep it to yourself for a second. So, There is a special case of this special case. There's always special cases, man. Physics loves special case. I'm going to get special case tattooed somewhere on me. I don't know where, but somewhere. To feel weightless. To feel weightlessness. What if it's even possible? Would it be possible? And if it is possible, what value would it be? Zero is, by possible you mean, is it a number that could happen? It is a number that could happen. Would it do this? You tell me. Remember, what factor in our equations, what variable told us our apparent weight?
How fast are you referring to velocity? Speed?
Well, no, because it says how fast must an elevator accelerate?
Oh, okay.
What if it's over G when you feel like you're being pushed like down?
Yeah.
Oh, you go like into
Well-
the ceiling. That's cool.
Wait,
Yeah,
I
I'm thinking of
understand,
those
like,
rides.
right now I feel
You're
like.
going down.
No, weightlessness means that you feel like you're floating.
Oh.
You guys have an answer? You do? Do you have an answer? Yes? I know he has an answer. Do you have an answer? Do you have a did you prove the answer?
Oh,
I wrote one squiggly left.
Oh my. Johnny, do you have an answer for me?
I didn't-
No. Did you do it?
Oh,
What variable did we have in our equations that represented our apparent weight? That Fn. And we saw, actually, to be fair, she put it in a great way. All of them kind of looked like Fn. That's a terrible n. Wow. Fn equals mg plus or minus something. That's really what we got, right? So if I want to be weightless, that means that I feel how much Fn? Zero. I feel no Fn. I'm floating. I'm not even touching the ground. So 0 equals mg plus or minus a. To be fair, a could also be 0, but then that kind of tells us some things. So that tells me that either m is 0.
why plus or minus?
Well, because if I'm accelerating upwards, then a is positive. If I'm accelerating downwards, then a is negative. And I'm covering my bases.
It can't be both.
No, it can't be both. But I'm covering my bases.
Okay, yeah.
I'm covering my bases here.
Could you feel weightless moving down, like you look up?
Well, that's what we're getting to. If we're moving upwards, that means that these numbers are getting bigger, not trending towards 0. So I could probably get rid of that. Making it positive is going to not make me good. It makes me heavier. Weightlessness is me getting or feeling lighter. So that's kind of the way I want to go. Okay? So this gives me two solutions. Either m equals 0, so you suddenly lose all of your mass, which would be weird. So that's not a very good solution. So a better solution comes from this guy. So when you accelerate downwards with a magnitude of g, you feel weightless. And that's how the Vomit Comet works. That's how those things work. There is a plane called the Vomit Comet that NASA uses to train astronauts. No, that's not the arm thing. But it's a plane that goes up into high atmosphere, right? Really high. And then starts crashing towards the Earth at that acceleration so that the people inside of the plane feel weightless. And that's how astronauts train for weightlessness in space. Even though it's not actually perfectly weightless in space or on this thing, but whatever. No. There are pilots actually flying this thing that are strapped down to their seats.
No, but the cool part that's
Oh,
all
they
the process
don't?
is on the
Wait,
way
how do-
up, they also
How
feel
do they
weightless
go
because
hit their
it's
heads on the plane?
decelerating downward. Like,
Yeah.
Not the whole leg up. But
Yeah, but they speed up on the way up. Then they start to slow down so that they can come back down.
How do they like lift off the seats and then crash up?
No, they're not.
They are okay.
Like they.
We don't have a lot of time, but
I can touch it. Yeah, I don't want to let this go.
this is still cool. And the next step is something that we don't have enough time to start anyways. So
Out to the floor. No chance.
This video was filmed in 2016. All right. Well,
Oh, it's like a big plane.
yes, that's why I meant. Well, that's what I meant when I said it's a big plane.
I didn't hear that part.
The plane follows a parabolic flight path to produce weightlessness. A typical flight consists of about 32 arcs. As the plane climbs towards the top of the parabola, passengers feel the
Parabola.
force of nearly 2 Gs, or twice their body weight. Once the plane starts to go over the top of the invisible arc and begins descending back toward Earth, flyers free fall, experiencing nearly 25 seconds of zero gravity. The passengers and any objects not nailed down are weightless.
You're floating there in the middle of the aircraft going, and your mind's kind of going all over the place saying, this isn't right. And you're just trying to, I guess, get your bearings all the time.
The plane is more commonly known as the vomit comet because of its reputation to wreak havoc on the human stomach.
Another man down, man down.
Each year, collegiate teams from all over the country submit proposals to NASA to be part of its Reduced Gravity Student Flight Opportunities Program. The space agency selects the top proposals.
For those of us.
Craig Sharp, Christopher Ubelacker, Jarrett Whetstone, and James Craven represent RIT.
Blew my mind when I first heard that we were going to be accepted into the project.
He's actually Wes Craven's brother.
But, it's completely worth it.
In July of 2008, RIT's team heads to Johnson Space Center for a week, which culminates in a climactic 90-minute flight to test an experiment in zero gravity. The RIT team's experiment looks at the feasibility of inkjet printing in a weightless environment.
We were testing the ability for inkjet printers, both piezoelectric and thermal print heads, to function in microgravity.
RIT is in great company with other big name schools invited to
I was
participate,
gonna say, like, wow.
including Texas A&M, University of
Because eventually we will need to get off of this planet, and a lot of the stuff that is out there is in zero G. I would like to be able to print things out when we ultimately live in space colonies. I'm just saying. I'm just saying. I mean, you're still going to have homework.
The health and safety of the students during flight is also of the utmost importance. As part of the pre-flight preps, the students
Well,
go into
so that's the vomit comet, and that's essentially the application of exactly what we just learned right here.
hypoxia. Twice her body weight.
Oh, I went back. Whoops. So just to wrap up, did I do it again? Yeah. So just to wrap up, these are questions 37, 39, and 40 in your book. I'm trying to find better ones that are more APE for weightlessness. There's better ones for centripetal motion that we're going to do tomorrow. Can we move this quiz to the beginnings of Friday so that we have time to do centripetal motion?
Yes.
Can we do that? Yeah.
Thank you so much.
I really want to make sure we get through centripetal motion, and I don't want to go through and do something without centripetal motion, because otherwise it'll be a drag question on the quiz, and I don't think anybody's going to be really happy about that. It's such a drag. So. Sorry. Yeah, please, lab, share it with me on Thursday. I think I'm done with your old labs, right?
Yeah.
Right? You guys all got, yeah. And you guys did anybody read the comments? Right? I went through and made comments. They were actually mostly really good. They were really good. So I was really happy with this. It doesn't matter because that's the only time you can use it. Like the only time you can get mu stat, it doesn't. Like no one calls it mu static max because there's no other value of mu static. So yes, you are technically correct.